Hello, and welcome back to Calero Academy. Today, we'll be doing the final installment of the question that asks us to find the plane that contains vector 1, these two vectors vector 1, which will equal 0, 1, and minus 2, plus t times 2, 3, and minus 1, moving to the left a bit, and vector 2, which will equal 2, minus 1, and 0, plus t times 2, 3, and minus 1. Note that this is the parametrized function form of the vector, where you can think of t as our x, 2, 3, minus 1 as our m, and over here 0, 1, minus 2 as our b, mx plus b, a special form of line. So, in the first two approaches, this is going to be approach C. In approach C, we're going to be using the dot product to try to solve this equation. In the first two approaches, we use the cross product, and then the 3 points approach. So this thing in the end, it'll be using as the trick we used in approach B with the 3 points. But in the beginning, it's really going to just resemble the same type of idea as approach A with the cross product. So this will be interesting. Without further ado, approach C. So, something interesting about the dot product is that if you take two orthogonal vectors vx and dot product vy, the dot product between the two perpendicular vectors is going to be equal to 0. So it seems like, of course, now we have the idea. We just need to find the normal vector. All we have to do is take a vector, another one of the vectors that we know lie in the plane, and dot product it. Let's remind ourselves of the equation of a plane. A outside of x, we're going to use the alternative form ax plus by plus cz plus d is equal to 0. We're going to be using the type of equation that we showed in approach B. So, what we do now is think for a moment. Consider the normal vector. There are an infinite amount of vectors that are normal to vector 1 or vector 2, the parallel. However, not all of these infinite amount of perpendicular vectors are actually perpendicular to the plane itself. Think of it this way. You have two vectors here, vector 1, vector 2, parallel, outside our plane. It stretches on for infinity. And then we have a perpendicular vector, our normal vector. This thing is inside the plane and it's perpendicular to these two vectors, v1 and v2. However, it's nowhere near perpendicular to the plane. It's inside the plane. By definition, it is not in any way perpendicular to the plane. So what we need to do, we need to counter this by creating multiple equations to find the normal vector. And we're going to do something similar to in approach A, and we're going to create another vector. This vector will be the one that connects the points 0, 1, minus 2, and 2, minus 1, 0. We solved that in the first video, and that's going to be equal to our new vector, vector 3, will equal 2, minus 1, 0, minus 0, 1, minus 2. That's equal to 2, minus 2, 2. T times that, plus some points, x1 plus x1, y1, and z1. So, that's in the form of a parametrized form. So, now let's try and solve. We have two vectors that we want to show that are orthogonal to n, and our simultaneous equation will be, we want to see that vector 3 dot product normal vector, v3 dot product normal vector is equal to 0, and that say v1, the v1 vector dot product n vector, the normal vector, is also equal to 0. Now we know what the slope of the vector 3 and vector 1 is, so we can plug that in immediately. This is vector, so this is going to be, sorry about that, it's going to be 2 minus 2 and 2 dot product the components of n, which will be a, b, and c. This is all supposed to be equal to 0. And the components of v1 are 0, 2, 3, minus 1. So that is 2, 3, minus 1, dot product a, b, and c. This is supposed to equal to 0. Okay. Now we're going to do something similar to what we did in approach B. We're going to use our lambda trick. So, what we do now is evaluate. So in this, the equation 1 is basically dot producting 2a minus 2b plus 2c is equal to 0, because that's all really the dot product does. It says times the x times these ones to each other, add the multiplication of the second terms, add the multiplication of the third terms, blah blah blah. So that's our equation 1. And equation 2 says 2a plus 3b minus c is equal to 0. Now, adding these equations will yield that 5b is equal to 3c, or that that b is equal to 3c on 5. And also putting that back into the equation after a little bit of algebra, we'll see that a is equal to minus 2c on 5. As you can see, we're following the footsteps of approach B. So, now, therefore, we can make our normal vector be equal to a is equal to minus 2c on 5, our b is equal to 3c on 5, and we haven't worked out c, because after all, that was 3 unknowns and 2 equations. But now we're going to do something similar to the trick we showed in approach B. So let's think. All we really want is a vector that's normal to the plane, and we have one here. However, we don't know what c is, so we can't really plug it into our equation yet. But we know that our vector, any vector n, any vector v, is going to be parallel to vector lambda v, where lambda is some constant. Because it doesn't change the direction of the vector v. All lambda does is change the magnitude of the vector. So it changes in size, the vector. The direction remains the same. So with that in mind, we can choose a lambda to multiply to all of these guys, to multiply to the normal vector, and that will change all the magnitude of the normal, but it will not change the direction. It will still remain perpendicular to the plane. So let's choose a lambda that will help us try to simplify and find z. Let's have, say, lambda c equals 5. Now, therefore, lambda n, the lambda multiplied by the normal vector, is equal to lambda times minus 2c on 5, lambda times 3c on 5, and lambda c. However, lambda is just equal to 5 on c, and what this will lead to, the normal vector multiplied by lambda will be equal to minus 2, 3, and 5. That is the slope of our normal vector, if you want to think of it that way. This is going to be these are going to be the components A, B, and C, which will satisfy the equation we have over here. That's all it is. Very simple and very beautiful also. So, now all we have to do is plug in back here and then solve for D. So we have minus 2x plus 3y plus 5z plus d is equal to 0. Now, before we go and celebrate, we still have to solve for d. So what we do, how we solve for d is that we just plug in one of the points into our equation and then solve for d. What we do now, let's just say select 0, 1, minus 2. So plug it into here and we'll find what d is. So that will be 0 minus 2 times 0 plus 3 times 1, 3, plus 5 times minus 2 minus 10 plus d is equal to 0. Or that minus 7 plus d is equal to 0. Or that d is equal to 7. So we have our equation that minus 2x plus 3y plus 5z. Sorry about that. It wasn't that clear for you. I actually didn't move it up enough for you. Sorry. So minus 2x plus 3y plus 5z plus d, which is in our case is equal to 7, is equal to 0. So we have found the equation of the plane that contains vector 1 and vector 2. Now, we have just done an amazing journey with our vectors. We have gone through nearly every single approach that I can think of. They're pretty much the only other approach that we could use to solve this equation, to solve this question, is to go through some esoteric madness like the quaternions, the precursor to vectors. So, thank you for watching. This has been a Calero Academy production. We hope that you enjoyed this video, and also Calero Academy will now start taking suggestions for videos in its comment section. If you want us to make a video of something, just enter it into the comment section and we'll see if we can make it.